cannot see, but yeah, okay.
I don't think it's recorded. Okay.
Now it's recording. Okay. So, good morning, everyone. We are Mo, Denzel, and Drew, and we are presenting our deep learning CA2. So I'll be presenting the part A, which is GAN, generative adversarial networks. So for the dataset, we pick Pokemon as it is interesting and fun, and we can also generate new Pokemons along the way. The dataset is gotten through this link, and that there are 819 Pokemon images in total in the dataset. So for our GAN, we decided to go with DC GAN, and we use PyTorch to implement it. So firstly, we have to do image augmentation as there's only 800 plus images, so we need to increase our training data set. So after doing it, we will have about over 2K plus images for the training data. Then to see our images, we need to denormalize it as it was normalized from the previous slide above. This code is to show the images, the training data. So this is the discriminator that we use. Its purpose is just to condense an image to a single value to tell whether it is real or fake. The discriminator features 5 convolutional layers and leaky value layers for activation functions. And batch normalization is performed after each convolutional stage, except for the output. This is our generator. It takes in what it does. It just takes in a random vector, then it converts it to an image. As you can tell from the name, it generates. And it is quite similar to the discriminator. It features convolutional transpose layers, which is used to upsample the random input vector into a full image. So this is the testing model. It's just to make sure that everything is in the correct size before we move on to train our GAN. So for the GAN training, we need to take note of these few things. You need to use a larger number of filters as it gives our convolutional layers more information, and hence being better for the GAN, and it will generate better images. And secondly, we must use smaller batch sizes. So and the discriminator can outlearn the generator quickly with large batch sizes. And 3, we need to keep the kernel sizes medium. And 4, slightly higher learning rates is better than super low learning rates. Okay, this is to set up our GPU in order to train our GAN. So this is to train our discriminator. The discriminator makes prediction on the real data and then the fake data being generated by the generator. Next up, we need to train our generator. So how we train it is the generator will read a latent batch, which is just a set of random input vectors. It generates the image, then it feeds them to the discriminator, which then will predict how fake the images are. So this to save the results so that we can view the results later. So this is our full training loop. This code is just to send our discriminator and generator to the GPU in order to do the full training. So for the training, we train with different epochs, 100, 150, 300, and 500. And now let's compare them with different results.
Okay, so I will be going through the training, the results of the training for 100, 150, 300, and 500. So for the results, right, at 100 epochs, some distinct Pokemons have been generated. You can roughly tell. Although some of them do not have a really distinct shape or color. And at yep, so at 150 epochs, next slide. Yeah, at 150 epochs, the results are a little bit better, as you can tell, at as compared to the 100 epochs, but there are still quite a few Pokemons, and there are more Pokemons with more distinct features. However, there are still a few Pokemons that like doesn't really look very from afar still doesn't look like a Pokemon. Right. At 200 epochs, there is a slight improvement only from 150 epochs, as the shapes and the features are more declined. However, some, as you can tell from afar, can't really tell it's a Pokemon. And then, so mode collapse occurs from 300 epochs onwards. The generator starts producing the same outputs from 300 epochs onwards. So these are the charts for the losses. So I'll be going through the 100 epochs chart, as it is a lot cleaner as compared to the 500. So the losses chart, in general, the losses for both models were relatively good throughout. The discriminator was prevented from hitting 0 by the noisy labels, which made it possible for the generator to not lose out over time. So these are the charts for the scores. Once again, let's look at the 100 epochs, and it is a lot cleaner. So over time, the discriminator is able to start to tell which Pokemons are real or fake. This is pretty good, but it could be a lot better if the discriminator could figure it out faster than the generator. Next slide. So our conclusion is the GAN managed to generate some unique Pokemons, but there can still be a lot more improvement, as most of these Pokemons that are produced are generally not game ready yet, but from afar can more or less tell, like if you were to stare from really far and like maybe squint at it, uh, you you might be able to label it as a Pokemon. So moving on to the next slide, our part B, our reinforcement learning, we decided to go with the Atari Bowling. And some background research, Bowling is a video game that was published by Atari in 1979 for the Atari VCS. It was programmed by Larry Kaplan, who left Atari to found Activision. And the game is the game is an interpretation of sport bowling, playable by 1 or 2 players. So in all 6 variations, game lasts for 10 frames or turns. At the start of each frame, the current player is given 2 chances to roll the ball down an alley, just like a normal game. In an attempt to knock out as many of the 10 bowling pins as possible. So the bowler may move up, down, left, right of his end of the alley to aim before releasing the ball. In 4 of the game's 6 variation, the ball can be steered before it hits the pin. Knocking down every pin on the first shot as a strike, while knocking down every pin in both slots is a spare. The player's score is determined by the number of pins knocked down in all 10 frames, as well as the number of strikes and spares acquired. So next slide. For the first model, a DQS agent is chosen, and it has worked for other Atari games such as Space Invaders, and if I'm not wrong, also for Pac-Man, I think. And I would like to pass on to Denzel to explain more on this sector.
Okay, thank you. No, next slide. Yeah. The test was tested with random choices, and if you look at the right side of the screen, the scores are not the worst, but they are quite random as there is no prior training. For building a model, 3 convolution layers and 3 dense layers were used. For building the agent, the build agent function is created in order to make the agent. And then the apps grid queue policy is passed into the linear annealed policy, and other parameters are also added. For the testing of the model, we tested the model with the DQN agent that was created in the last slide, and the scores turned out pretty good. This time, the model is tested with the safe weights, and the score increased from 87 to 108, which is pretty decent, which is quite a high increase. Yeah. The model might, in conclusion, when looking at the model might yield good results, but the game is not able to be displayed on Google Colab, so we cannot really see its performance. Next, we'll be looking at the models using stable baselines tree. Next advantage, actor critic A2C agent is used for the Atari game. The baseline model is without any other modifications. It has a low yield score of 12. For the baseline model with 50,000 time steps, the score is much better as it increased from 12 to 33. The model is improved as more parameters are added and modified. There's a slight improvement as the score increased from 33 to 39 when using MLP. The model is then improved using MLP with 50,000 time steps. Once again, the time steps are increased to 50,000, and there is an improvement as the score increased from 39 to 51 this time. This time we used the CNN policy instead of the MLP policy. It yielded a score of 25. This time we increased the time steps again to 50,000. However, there is virtually no improvement as the score only increased by 1. The conclusion for part B is that the DQN agent did have a decent score, but it does not show how the AI actually performs. The A2C agent, on the other hand, did not have good scores, but is able to display how the AI performed. There were many challenges as reinforcement learning is a new thing, so there are less resources. We've come to the end of the presentation. Yeah.
Thank you for listening to our presentation. Yeah.
Okay, we are done with